Space, a vast frontier still largely unexplored, beckons us with new challenges and opportunities for discovery. In this program, we'll get an idea of just how big space really is and how we measure it. We'll take a look at Einstein's theory of relativity and find out what implications it has for space exploration, space travel, and everyday life on Earth. How big is space? Most of us have some concept in mind. For example, you've probably heard that space is infinite, or that we can see billions of light years into the distant past of the universe. We do know that space extends in all directions as far as we can see with the most powerful telescopes. But is it really infinite? Are there ways we can measure just how big it is? The Hubble Space Telescope and others like it have allowed us to see billions of light years into space. The galaxies in this image are almost 14 billion light years away, but these galaxies are actually much further away now because of the time that has passed since the light we are seeing left them.
If the universe were just static and not expanding or moving, you could say, well, that time we're looking out to was about 14 billion years ago. So light travels at a constant speed, and you could say that that distance is 14 billion light years. The problem is that ever since that light left that place in space, the universe has expanded. The calculations based on how fast we think the universe has been expanding over time have given us a rough estimate of the diameter of the visible universe. It's probably around 150 billion light years is the diameter, so that's as far out as we can see.
How do we know how far away objects in space really are? And how are those distances measured? On Earth, distances are typically measured in miles or kilometers, but these units aren't meaningful in space. For example, the distance from Earth to Proxima Centauri, the nearest star, is almost 26 trillion miles. Does a number of that size have any meaning for you? It doesn't for most people, including space scientists. In order to simplify their work, they use units of measurement more appropriate to the vast distances of space.
Well, the reason astronomers pick different measures of distance in the universe is because the universe gets really big really fast. And if you don't want to use large numbers and talk about large numbers and multi-syllabic numbers, you kind of keep inventing a larger and larger yardstick that you can measure by.
For distances within our solar system, scientists use a measurement called the astronomical unit, or AU. An AU is defined as the average distance between the Earth and the Sun, or about 93 million miles. While the AU is convenient for use within our solar system, distances between stars are so great that other units of measurement are needed.
One of them is kind of commonly called the light year, and this is the distance that light travels in 1 year. It's around 5 trillion miles, and it is simply, if you take the speed of light and multiply it by a year, you get a distance. That's what a light year is.
A parsec is another unit of measurement that astronomers frequently use. A parsec is equal to 3.26 light years, or about 19 trillion miles. 1 parsec of distance is defined by a right-angled triangle, where the base is the distance from Earth to the Sun, or 1 AU, and the acute or parallactic angle is 1 arcsecond. For example, Proxima Centauri is 4.3 light years, or about 1.3 parsecs away. Our own Milky Way galaxy is about 100,000 light years, or 30,000 parsecs across. The Andromeda Galaxy, the closest spiral galaxy to our own Milky Way, is 2.3 million light years, or 700,000 parsecs away. Can you imagine any of those distances in miles or kilometers?
A parsec is a unit of distance that astronomers use, and it's useful to astronomers mostly because of the way it's measured, and that is by parallax. Parallax is this effect where if you look at an object which is some distance away from you and you move a little bit, the object will appear to move with respect to objects in the background. So that's called parallax. You can see that simply because we have two eyes. If you close one eye and hold your thumb out, and then switch your eyes back and forth, the thumb will move. And if you move your thumb close to you, your thumb moves a lot when you do the switching. And if you move it far away, then the thumb moves a little bit.
Just as with the thumb experiment, scientists can use parallax to measure distances in space. For example, the distance from our sun to various stars. For a parallax measurement, astronomers use 2AU, the distance across Earth's orbit, as the base of a triangle. They then take two pictures of a star, 6 months apart, one from each side of Earth's orbit. By measuring how much the star appears to move from one picture to the other, they can calculate alpha, the angle of apparent motion, which is measured in fractions of an arcsecond. A straight line from the sun to the star creates two right triangles. This divides alpha in half and yields the value of the parallactic angle. Remember the parsec? Using the value of the parallactic angle and the distance from the Earth to the Sun, scientists can then use a little trigonometry to find the distance to the star. Although the parallax method works well for stars closer to Earth, this technique is limited by the size of the Earth's orbit and by the atmosphere, which blurs any parallax less than 1/50th of an arcsecond. So, for stars or other objects more than 50 parsecs or 160 light-years away, still other ways of measuring distance are needed. Almost all distance estimates in astronomy rely on first measuring the distance to nearby objects, then using some property of these objects to extend the distance to farther objects. There are several ways to do this. For nearby objects, the simplest is the parallax method, which we've already seen. A second method is to measure a star's brightness and use that to estimate the distance to it. If we know both a star's intrinsic or actual brightness and its apparent brightness, how bright it looks from Earth, we can use these values in a simple mathematical formula called the inverse square law of light to find its distance. It's easy to measure a star's apparent brightness from Earth, but how do we find its intrinsic brightness? Bright stars that are far away may appear dimmer than less bright stars that are closer to us. To find a star's intrinsic brightness, scientists first record its color and spectrum. A spectrum is nothing more than the light from the star broken into its various component wavelengths. Each star has a unique spectrum that tells a lot about its size, age, composition, mass, and brightness. The color of a star indicates its temperature. Once astronomers have a star's temperature and spectrum, they use a tool called a Hertzsprung-Russell diagram to find its intrinsic brightness. A Hertzsprung-Russell diagram is a plot of stars whose temperature, distance, and intrinsic brightness are already known. As you can see, most stars on this diagram are clustered in a diagonal pattern called the main sequence. These are stars in the most stable part of their existence. There are also clusters of red giant and supergiant stars, and white dwarfs. With a star's temperature and spectrum, scientists can determine where it falls on a Hertzsprung-Russell diagram and find its intrinsic brightness. A star's intrinsic and apparent brightness are then entered into the inverse square law of light formula to calculate the distance to the star. Once we get out of our own galaxy, distances get harder to measure. Parallax no longer works, and it's often impossible to gather a clear spectrum of a single star to estimate intrinsic brightness, so other methods must be used. The first uses a type of star known as a Cepheid variable. These stars have very regular periods of fluctuating brightness. The longer the period, the brighter the star. When a Cepheid variable star is located, its period is used to calculate its intrinsic brightness. Then its intrinsic brightness and apparent brightness from Earth can be used to estimate its distance. Cepheids are one of the ways we can measure the distance to nearby galaxies. This method allowed astronomers to take another giant leap by measuring the speed at which galaxies are moving away from our own Milky Way.
One of the things that you can do with spectra, besides being able to tell, for instance, what elements are in an object, is you can tell whether or not that object is moving toward you, moving away from you, and how fast it's doing that. It's an effect called the Doppler effect. And it's a pretty common effect. People experience it all the time in their daily lives. They just don't realize it. It's really noticeable in the sound of sirens on an ambulance. As the ambulance is coming toward you, you hear the pitch of the siren rise, and then as it goes past you, you hear the pitch drop. And the idea is that anything that's giving out waves, like sound waves, for instance, if the object is moving toward you, it kind of piles up toward the waves that it's already sent out at you, and the waves get shorter and shorter. So in sound, short waves mean high pitch. And then as it goes away from you, it's actually moving away from the waves that it sent at you, and so the wave crests or troughs, if you think about them, spread out as they're moving toward you. And spread out waves in sound anyway is lower pitch.
The same kind of thing happens with light. When an object moves towards us, its light waves get squished together, shifting the light toward the shorter wavelength, the blue end of the spectrum. When it's moving away, light becomes redshifted, moved toward the longer wavelength, the red end of the spectrum. Edwin Hubble, the astronomer for whom the Hubble telescope is named, discovered what is now known as the Hubble law. The farther away a galaxy is from us, the larger its red shift. The red shift is also interpreted as the speed at which a galaxy is moving away from us. Hubble found that the light from virtually all galaxies was shifting to the red. Because of this red shift, it appears that they are moving away from us, and the universe is expanding, which is exactly what is predicted by the Big Bang theory of the origin of the universe.
You'd expect things to be just kind of dancing around randomly, but that wasn't the case. We found galaxies were generally all moving away, and the farther away they were, the faster they were moving. And so that was what eventually became called the Hubble law.
Using the Hubble law, scientists can now determine how far a galaxy is simply by measuring how fast it is moving away from us. This works out to distances of many billions of light years. But for the most distant galaxies, astronomers look at supernovae to determine distance. A supernova is an exploding star that is so bright it can be seen clear across the visible universe. To determine the absolute magnitude of an observed supernova, its spectrum is compared with one from a known supernova nearby. Scientists then use a form of the inverse square law of light formula to estimate the distance to the supernova.
Well, it turns out that not every single supernova explosion is going to be exactly the same brightness, but it turns out that there's a way to kind of calibrate it. You can look at how long it takes the star to actually dim down after its initial outburst of light, and it turns out that you can kind of calibrate and figure out, based on how long it's taken for it to dim, you can figure out how intrinsically bright it was when it first went off, and then you can play the game of figuring out, or saying, okay, I think I know how intrinsically bright it is. I've measured how bright it is here on Earth, and therefore its distance must be such and such.
So, how big is the universe? So far, we've seen objects about 14 billion light years away. How much larger the universe is and whether it is really infinite remains a question for generations of scientists to come. While astronomers continue to learn more and more about the size of the universe and the vast distances involved, exciting questions remain. To find the answers requires an understanding of the theory that completely changed the way scientists think about the physical universe and impacts almost everything they do: Einstein's theory of relativity. Albert Einstein, probably the most famous physicist of the last century, has had a profound impact on our concepts of the physical universe. Einstein's theory of relativity set the stage for a major shift in how we view our universe in terms of space, time, matter, energy, gravity, and acceleration. And its predictions impact virtually everything we do in space science. It has two parts: the special and the general theories of relativity. Special relativity states that space and time are not distinct and separate entities, but rather together they make up a continuous four-dimensional fabric called space-time. So distance can now be thought of as how far you travel through both space and time. Think for a moment about what that means. Imagine a space traveler, Jean, in her spacecraft, ready to blast off. To us, she appears to be stationary, but she is actually moving through time. In fact, all of her movement is through time. After leaving the Earth, Jean is traveling at 70% of light speed. Some of her movement through time is now diverted to her motion through space. What does that mean? Let's synchronize Jean's clock with the one back on Earth. Then we'll start both clocks and see what happens. To an observer back on Earth, time continues to pass at the same rate it always has. But when he looks at Jean's clock, it seems to be running slower than the one on Earth. Why? Because according to special relativity, neither time nor space are absolute, but can be converted back and forth into each other, depending on the motion relative to the observer. Yet for Jean herself, time appears to be running at the same rate it did back on Earth. Jean is showing an effect called time dilation, which we'll look at more closely in a moment. Prior to relativity, people believed time to be absolute. Clocks ticked at the same rate regardless of their location and motion. They could be in San Francisco, Paris, or on the moon. Einstein's special theory of relativity changed that notion.
When we have an object which is moving, relativity theory tells us that its clock runs more slowly. This is an effect that we call time dilation. It is nothing we experience every day. It's a completely counterintuitive concept.
Let's see how time dilation might work in interstellar travel. Imagine that Jean, the intrepid space traveler we met earlier, is one of a pair of twins. Both she and her brother John are 20 years old when she leaves on her trip to the nearest star. John remains on Earth, as Jean travels at 70% of light speed. When John has waited for 11 years, Jean returns. John is now 31, but to their mutual surprise, Jean is only 28. According to Jean's clock traveling at 70% of light speed, her trip took only 8 years. Motion slowed her clock by 3 years.
In addition to that time dilation effect, there's another interesting effect that comes out of relativity, and that is that space actually contracts when you have a moving observer.
Let's look at Jean's interstellar flight. Jean starts out traveling at about 10,000 miles per hour. On the moon, an automated camera there snaps a picture as she flies by. As she approaches Pluto, Jean is traveling at 90% of light speed. A super high-speed camera on Pluto snaps her picture as she passes by. In the picture taken from Pluto, Jean and her spaceship look squished. But in the one taken from the moon, Jean and her ship look normal.
This shortening or space contraction happens along the direction of motion. So that's what you would see from the camera that's on Pluto.
In addition to time and motion, special relativity addresses the relationship between mass and energy, which is summed up in the famous equation E equals mc squared, where E stands for energy, m for mass, and c the speed of light, which is a constant. This means that when an object like the sun gives off energy, it loses mass. How much mass?
If you were to take a chunk out of the Earth that's 1 football field long, 1 football field wide, and 1 football field high, that's how much mass the sun is losing every second.
In general relativity, Einstein introduced gravity and acceleration to space-time. In general relativity, Einstein showed that large masses distort the space-time continuum in such a way that the motions of small masses will be affected. At the basis of the general theory of relativity is the idea that gravity and acceleration are essentially the same, indistinguishable. For example, visualize 2 people, each in their own elevator. One elevator is at rest on Earth. The other is accelerating as it travels through space. The person standing in the elevator on Earth would feel the normal pull of gravity toward the floor. The person in the elevator accelerating upward through space would also feel the pull of gravity. Lacking visual cues outside the elevator, there would be no way either person would be able to distinguish between Earth's gravity and the effects of acceleration.
General relativity also told us something astounding about light, and that is that because a mass curves space and time, a light ray, which we used to think of as traveling in a straight line, now travels in a curve as it goes through this curved space. And so when you have a large mass like the sun or a star or a black hole, then space is so curved that light is very curved in its path as it goes around the star or the black hole. The larger the mass and the closer you get to it, gravity becomes stronger, and then you get greater curvature of space-time.
In the case of a black hole, its effect on curving the fabric of space-time is so great and its gravity so strong that light passing too close cannot escape. Relativity also has implications for interstellar travel. To get to another star within a human lifetime would require going unimaginable distances at enormous rates of speed. To put the distance and speed issue in perspective, let's consider the NASA Voyager 1 spacecraft. Voyager 1 left the solar system at a speed of 37,000 miles per hour, the fastest speed yet attained by a spacecraft. Yet even at this speed, it would take Voyager more than 70,000 years to reach the nearest star. Any interstellar spacecraft would have to travel much, much faster than this to make the journey in a human lifetime. But is it possible to travel at light speed or even faster?
According to the special theory of relativity, we can't get anything to travel at the speed of light or faster. What Einstein told us through the special theory is that as you try to accelerate an object, it takes more and more energy to accelerate it even closer and closer to the speed of light. In fact, if you calculated how much energy would it take to accelerate a mass up to the speed of light, that energy would be infinite, and so it's just not possible.
But relativity isn't limited to space travel. It actually has direct applications for your everyday life. Here's an example. The Global Positioning Satellite System, or GPS, provides satellite navigation for both civilian and military use. Pilots use the system to keep their planes on course. Within a few seconds, handheld GPS units can give you your longitude, latitude, and altitude to an accuracy of a few meters. A GPS receiver in a car can give accurate readings of position, speed, and heading in real time. To achieve this level of precision, each satellite carries an atomic clock that ticks with an accuracy of 1 nanosecond, or 1 billionth of a second. Each of the 24 satellites in the GPS system orbits the Earth once every 12 hours at an altitude of about 20,000 kilometers. Because the satellites are in constant motion relative to observers on the Earth, effects predicted by the special and general theories of relativity must be taken into account.
In order to understand the GPS satellites, we have to take both special relativity and general relativity into account. Special relativity tells us that because the satellites are moving with respect to us, their clock should appear to be running slower. On the other hand, general relativity tells us that because the satellites are in a weaker gravitational field, their clock should be running faster. We have to take both of these effects into account if we're going to use the GPS satellites. In fact, if you got everything synchronized up and didn't take relativity into account, within a few minutes you wouldn't even be able to get a navigational fix. And if you kept ignoring relativity, you'd be off by 4 or 5 miles every day.
There is another intriguing prediction derived from relativity theory for traveling across the galaxy: wormholes.
When you study the mathematics of black holes, it appears that black holes connect up vastly different parts of our universe, or maybe even our universe connected up with other universes, through these passageways that are called wormholes. And it kind of looks like you could travel through these wormholes, like a shortcut. Well, it turns out that it's not so simple. The wormhole might exist mathematically, but if you actually jump into a black hole and try to travel through the wormhole constricts, and it closes off before you can get through it.
So for the time being, travel to the stars doesn't lie with wormholes or travel at light speed or even near light speed. But imagining what could be is often the inspiration for making the impossible possible.
As long as we keep asking good questions and use our imagination, then someday we may travel to the stars.
Space presents a limitless frontier for exploration and discovery. Are you up for the challenge?